Good afternoon, everyone. I'm Renee Smith with Virtus Nutrition and host of the Fatty Acid Forum. Welcome to our 6th webinar entitled Forage Lipids, More Than You Think by Dr. Tom Jenkins of Clemson University. We at Virtus Nutrition believe that fatty acids matter. While fat typically makes up a small percentage of the diet, the impact fatty acids have on production, cow health, and dairy profitability are tremendous. That is why 1 year ago we launched the Fatty Acid Forum with the idea of creating engaging webinars to make the information on fatty acid nutrition more accessible and applicable to the dairy nutrition community. Over the past year, we've held 6 webinars that have been watched by several thousand people online and have generated much discussion and learning in this important area. Now it is my pleasure to introduce to you today our featured contributor, Dr. Tom Jenkins from Clemson University. Dr. Jenkins really needs no introduction to this group, as he's contributed to many of these webinars and is directing the curriculum for the Fatty Acid Forum. His list of research accomplishments is long, including major developments in the area of fatty acid analysis and in understanding pathways of biohydrogenation in the rumen. Also, a big thanks to Dr. John Andre, a forage specialist at Clemson University, for his contributions to this webinar's content. With that, I would like to welcome Dr. Jenkins to lead this discussion on forage lipids. As a reminder, please feel free to type in any questions you have in the box in the lower right-hand corner of your screen during the webinar, and Dr. Jenkins will address those questions at the end. Thank you, and now, here's Dr. Jenkins.
Thank you, Renee. Dr. Andre and I are thrilled that Virtus has given us the opportunity to share a few of our thoughts on lipid contributions coming from forages. Without a doubt, forages contribute immensely to the nutrient supply of dairy cattle to sustain growth, reproduction, and lactation. When asked about the nutrient supply coming from forages, most nutritionists readily acknowledge ample nitrogen to meet protein needs, energy contributions from soluble sugars and fermentable fiber, and in many cases, there are also a significant supply of vitamins and minerals. For the most part, though, forages are not recognized as a source of lipids. Now, this invisibility of lipids in forages, we think, is fueled or driven by the very low concentrations we continue to see for hay in most of our nutrition libraries. Now, here's an example of that, taking lipid data for alfalfa hay, mixed grass hay, and orchard grass hay from CPM for Dairy and from NRC for Dairy 2001. Ether extract values in both cases range from a low of about 2% to approximately 3.5%. Now, fatty acid values that are shown in CPM for the same foragers are much lower, and we expect that because fatty acid analysis does not include non-lipid contaminants that are included in ether extract. So the fatty acid values are ranging from about 1.5% to a little over 2%. So for the most part, we're used to seeing fatty acids in hay that range somewhere between 1.5% and 2.5% of the dry matter, obviously much lower than fiber and protein concentrations that we're used to seeing. And again, we think these low levels mislead us into thinking that forages in general and across the board are always very, very low in fatty acid concentrations and contribute little to the lipid intake of animals. Now, we have done some analysis ourselves at Clemson, and it's been shown by others as well, that fatty acid levels can reach much higher levels. Here's one example of this, where we took clippings from several forage species grown at an early vegetative, early maturing stages in field test plots at Clemson University. And in the case of the clover, alfalfa, and crimson clover, the values were running in the 3 to 4% range. And if you compare that to hay, and we'll use an average value for hay of 2%, and that's kind of our benchmark, then among these three, we're running about 2 times higher than the hay. Now, for wheat and ryegrass, we were seeing values in the 6 to 7% range, 3 to 3.5 times higher than what we're seeing for hay. Now, another example of this are results from another study done at Clemson University and published in 2009, where we grazed lactating cows on rye starting November 18th of 2007 to March 17th of 2008. And at the starting the grazing period, we were seeing fatty acid levels in the rye that were 6.8%. Now, by the end of the grazing season, they had declined to 4.7. Now, I should note that we took special precautions to be able to protect the lipids and see numbers this high. Once we clipped the samples, we immediately immersed them in liquid nitrogen, took them back to the lab, stored them at -80, and then eventually freeze-dried them for later analysis. Now, we realized that if we hadn't done this, clipping the plant, letting it dry or partially dry would have activated enzymes that would have caused extensive lipid loss. So we think by going through that procedure, we saw the best picture that we could get of what cows actually see when they consume fresh forage in grazing situations or perhaps green chop. Now, in this same study, after the end of the rye grazing, we then put them on annual ryegrass. Fatty acid levels, in fact, started at 4.5% and declined to 1.8% by the end of the grazing season. Now, the question is, seeing values as high as 6.8%, is this a lot of fatty acid? Well, to put it into perspective, this is data taken from a journal dairy science article where they fed 2 diets, a control with no added fat and one with 5% added soybean oil. And the addition of the soybean oil in this study was reported to cause a numerical decline in intake and likewise for milk yield. It also caused milk fat depression, causing milk fat percentage to drop from 3.53 to 2.73, and then it followed there was also a significant drop in milk fat yield. So by all definitions, this would be considered a high-fat diet for a dairy cow. This was a conventional TMR with half forage and half grain. Okay. And in fact, it had too much fat in it based on the setbacks on lactation performance. Now, we're not suggesting that this level of fat always leads to production problems, but it did in this case in an example of what most would classify as a high-fat TMR for dairy cows. What's interesting is the fatty acid level that they reported for this TMR in this study was 6.8%, exactly what we saw for the cows grazing the rye in that Clemson study from 2009. So it's just an example of there's instances when animals are strictly on forage and can have fatty acid concentrations and lipid intakes that are exactly the same as what we would see for high-fat TMRs. Now, we're also seeing considerable variation in fatty acid levels in fermented feeds. These are some data for unsaturated fatty acids that were reported in a recent study from 2012. And for grass silage and corn silage samples that were taken in a survey across the Netherlands. And for the grass silage, unsaturated fatty acids averaged about 1.5% from a low of 0.5 to a high of 2.8. That's a huge spread. And 2.8% unsaturated fatty acids is quite a high number. And went even higher for corn silage, averaging 1.61, going from a low of 1 to a high of 3.5. Now, if it's 3.5% or 3.4% unsaturated fatty acids, total fatty acids were approaching 4, and ether extracts could be expected to be well over 5. So those numbers are much, much higher than what you would find in most of these nutrition libraries, indicating that there's many cases where we underestimate lipid intake from forages, and we need to do some forage analysis when we're trying to diagnose certain lipid intake-related problems, such as milk fat depression. Next, we wanted to briefly show differences in fatty acid composition among forages, grasses, legumes, and compare it to corn silage. And we've grouped the saturated fatty acids together just for simplicity and show individually the oleic acid content, or 18.1, 18.2, which is linoleic acid, and 18.3, which is linolenic acid. And you can see that the legumes and the grasses have much higher concentrations of linolenic acid, or 18.3, compared to corn silage. Corn silage profile would be very similar to soybean products as well. And then next in the legumes and grasses, the 18.3 is followed next in abundance by linoleic acid, or 18.2, with much smaller amounts of 18.1. Now, the corn silage differs in that the predominant fatty acid is linoleic acid, followed next by oleic acid. So the legumes and grasses bring in a unique supply of fatty acids in more of the 18.3, which is an omega-3 fatty acid. Much smaller amounts of the omega-3 linoleic acid in the case of corn silage and soybean products. Now, the total fatty acid book values are shown at the bottom as well. What we rely on for the fatty acid composition and fatty acid contents for these forages is very much a function of a number of factors that cause variability, including the genetics of the plant, but even more important are environmental effects, including the effects of light, cutting interval, season, and fertilizer regime. And not to mention the preservation methods that we choose or the method of conservation. Now, let me quickly give an example or two here, starting with season effects. It's been reported in a number of studies that total fatty acids in forages are higher in the spring than they are in the fall. Now, using perennial ryegrass as an example, some data showed 3.2% total fatty acids in May in the perennial ryegrass, but much, much lower, only 1.2% in second regrowth. Okay? Now we're getting down closer to hay levels. And differences in fatty acid composition as well, with linolenic acid decreasing over summer, while palmitic and linoleic acids increased. Now here's two studies done in 2001 and in 2003 that examine the effects of regrowth on perennial ryegrass. Total fatty acids as a percent of the dry matter considerably were lower on the longer 33 to 38 day regrowth period than they were on the shorter 20 to 23 day regrowth period, and this was reflected also in the concentrations of linolenic acid that were present. And these numbers are effects that are not reflected in our nutrition libraries, and then once again, using standard library numbers can mislead us in terms of total fatty acid intake. Here's one more example. It's the effect of partial drying or wilting. Two separate studies, once again, consistently have reported a decline in total fatty acids in going from unwilting to wilted. And once again, this was reflected by lower levels of linolenic acid as well. It's been reported that and shown that drying the plant, even drying for haymaking and going further than wilting, it can even cause greater lipid losses occurring in the plant. And that's because the drying process activates enzymes that causes oxidative loss of polyunsaturated fatty acids, but it can also activate plant lipase enzymes that can cause accumulation of free fatty acids that we'll talk about more here in just a minute. Now, the whole story is just not about the amount of lipid that's in the plant, but it's also about the availability of the lipid. And I want to say a few things about availability, or what I'm going to refer to as lipid release. And I'm talking about two things here. Talking about release from plant structure and release from lipid structure. And in both cases, faster and more extensive release will equate to greater potential to disrupt rumen fermentation and then ultimately have impacts on lactation performance of the cows. So as an example, if you add 1 pound of corn oil to a TMR, okay, it's on the surface of the plant, being immediately exposed to the microbial population in the rumen, okay, and in that instance we can imagine a high availability. Now that corn oil immediately exposed will have much higher potential to disrupt microbial population and affect fermentation. Now, if you feed the same amount of corn oil in the form of corn silage, and it would take 20 or 25 pounds of corn silage, dry matter, to do it, not unusual, now the lipid is tied up within the fibrous matrix of the plant, not readily and available and immediately available to the microorganisms when it hit the rumen. So there would be slower release from the plant structure. It's metered out. It may be eventually released to the same extent as corn oil, but at a slower rate, and we think that helps to lessen its impact on fermentation. Now, one more example would be oil seeds, and using cottonseed as an example, by nature of its hard outer seed coat, we can imagine it would have a much slower release and exposure to the microbial population and might be classified as low availability. Now, we have not been taking measurements of lipid availability or lipid release to any great extent, but we have been paying attention to starch and protein release, especially from fermented feeds. And here's some data in feedstuffs from a few years ago that show the effects of ensiling period, increasing ensiling period, and moisture content on changes in high moisture corn digestibility. And as the ensiling period increased, we can see in general that there was an increase in the digestibility of the high moisture corn, which could be explained by the fermentation process exposing or opening up the corn more to the microbial fermentation enzymes in the rumen. We could also see from this data the effects of moisture as we go from 24% moisture in the case of the green line to 28 to 30 to 35% at the top. We're talking about a much greater increase in the digestibility of the high moisture corn. Now, we think that lipids may behave the same way in higher lipid availability, greater release with the fermentation process. Now, the other aspect is lipid structure release. Now, fatty acids in the plant exist in the bound state or in the free state that we refer to as free fatty acids, abbreviated FFA. Now, if they're bound mainly in the form of glycerol, other compounds as well, but mostly glycerol. And if they remain bound to glycerol when they're in the rumen, they'll have very little effect on rumen fermentation. Now, there are enzymes that operate to release them from the glycerol. These are referred to as lipases. They can be lipases that are produced by the plant that releases them from this bound state in the plant before they're ever consumed by the animal. Okay? So they're going to hit the rumen already as free fatty acids. Or they can remain bound in the plant, hit the rumen, and bacterial rumen lipases will release them from that bound state. And the more fatty acids you have released or in that free fatty acid, and the quicker that they are released, the greater the potential to disrupt rumen fermentation. So, as an example, these are some data from a couple recent studies showing free fatty acid levels in fresh ryegrass, timothy, and red clover, and you can see that the free fatty acids are typically low, less than 10%, a little bit higher in the case of timothy. Ensile them now, and the free fatty acid levels increase considerably, reaching as high as 3/4 of the total fatty acids in the case of the ryegrass, and half or more across the board. So these are accumulation of free fatty acids that's occurring in the plant even before it's consumed by the animal. So these are hitting the rumen already released. Now, microbial enzymes will go on to release them too, but we think this immediate release and this immediate exposure as free fatty acid to the microbial population can have more impact on rumen fermentation. So once again, it's not just about the lipid content that's important, but the form that it's in as well. I want to give one more example of this before finishing, and it's an example with whole cottonseed, work that was done at the University of Georgia at Tifton. And they had 3 different whole cotton seeds. One was classified as normal because it had normal less than 10% free fatty acid level and about 18% oil. But they found 2 other whole cottonseed sources that had 4 times the normal amount of free fatty acid. One of them had visible signs of overheating, and that might have explained the higher free fatty acid. The other is no signs of overheating, and not exactly sure what caused the accumulation of free fatty acids. Now, when these were fed to lactating cows, there was no effect of the 3 diets. The 3 diets were exactly the same except for the source of cottonseed. And there was no effects on intake or on milk, but there was a rather significant milk fat depression caused by the 2 that had the free fatty acid content. And the diets were identical in all ways, so the only explanation is the higher free fatty acid content that we noted here. Milk dropping from 4.22 down to 3.6%. So it's an example, once again, how this release that occurs in the plant can have an impact on rumen fermentation process, and in this case on causing milk fat depression. So we wanted to make 3 major points today. The first was that fatty acids in some early vegetative grasses and legumes are comparable to many high-fat TMRs that are fed to dairy cows. So there are instances in early maturing early vegetative stages, forages, that can have very high lipid levels. Also, ensiled forages, including corn silage, have wide variability in their fatty acid content, and you can't rely just on book values all the time. You might have to have them analyzed when you're diagnosing problems. And this can go on to define the amount and type of lipid consumed by the cows. And then the third and final point is that changes in the amount and characteristics of forage lipids over time can play a role in determining the overall diet effects on rumen function and lactation performance. So once again, we thank you for your time and your attention, and we thank Bertus for giving us the opportunity to share our views on this, and we're going to turn back to Renee if any questions have come through. Thank you.